Okay, let's do another example. Okay, let's now compute the equivariant cohomology of the sphere under the rotation action. Okay. So equivariant. Okay, so I have the two sphere, and I rotate it about the z-axis, okay, and therefore the group is S1 and the manifold is S2, okay, and so we want to compute the equivariant cohomology of S2 under the S1 action. Okay, and this, by definition, is the cohomology of the homotopy quotient S2 by S1. Okay. And now, what's the definition of the homotopy quotient? What's the definition of this? How do you construct a homotopy quotient? Yeah. You find a contractible space. Yeah, you take the product with the manifold, and then you take the diagonal action, right? So you need the contractible space on which S1 acts freely. That's ES1. That's what we call ES1. You take the product with S2, and then you take the quotient by S1 under the diagonal action, okay? And what's ES1? What's the contractible space on which S1 acts freely? S infinity. So this is S infinity cross S2. And then we often put the S1 down here. Okay. So that's what we have to compute. Okay. Now, by Cartan's mixing diagram, so you have S infinity cross S2, and then the two projections, and then you have the quotient by S1, and the two projections. Let's see, this was S infinity to, what's the base of ES1? That's CP infinity, right? And then here you have just S2 over S1, okay? That's Cartan's mixing diagram. And you know that this is a principal S1 bundle. So what is this? It's a fiber bundle with fiber S2 up there, okay? So we have a fiber bundle with fiber S2. There is a fiber bundle. Okay, so mg, it's always this, mg over g with fiber m. And in this case, it's S infinity cross S2 over S1 over CP infinity, and the fiber is S2. Okay? Well, we have this fiber bundle. Okay? And we want the cohomology of the total space. We know the cohomology of S2, and we also know the cohomology CP infinity, if you just generalize what we did. So we know, okay? Now the cohomology of CPN, if we generalize the cohomology of CP2 to CPN, you see that you will just have to go a little bit further, right? So you will get ZU, and then for CP2, it's U3 is equal to 0. For CPN, it's going to be UN plus 1. Okay. And then for CP infinity, well, it never stops, so it's just ZU. Okay? Now, these two results, I want you to write out all the details for, so that's one of the problems in the problem set. We know from problem set 2, okay? We know this. Yeah, so that means you have the cohomology of the base and the cohomology of the fiber, okay? And so you have E2, and then we just apply the spectral sequence to get E infinity, okay? So, all right, so E2. So by the ray, so E2 is the cohomology of CP2, just a minute, CP infinity tensor with the cohomology of S2, okay? And that's going to look like this. Zero, 1, 2, 3. 0, 1, 2, 3, 4, 5, 6. Here you have the cohomology of CP infinity, and then the 0th column is the cohomology of S2. Okay. So the bottom row is going to be, I'm just going to write down the generator. Okay. So that means it's Z times 1, and then here is U square, U cube. And the cohomology of S2 has one generator in dimension 2. I'm going to call that Y. Okay, and then it's 0 here. Okay. And so it's going to be 0 here throughout. And then what's this? Uy. Okay. You take the tensor product, so it's got a single generator. U squared y, U cubed y. Okay. And then everything else is 0, right? Now this is E2. This is E2. And now let's look at D2. So D2 goes down 1 and across 2. Okay? Yeah. So D2, well, it's going to be 0 on the bottom row because it goes outside the first quadrant. Okay? So these are all 0. And then here is 0. So D2 on this will be 0. Now this one, where does it go? It goes down 1 and across 2. So it goes here. So it's 0 because it goes into a 0 box. Where does this go? Well, it goes into a 0 box. So it's 0. This goes here, it's 0. Well, you see, D2 is 0. And it's for a very trivial reason, for dimension reason, for degree reasons. It's because you have only 2 non-zero rows, and they are in even dimensions, and D2 will go into an odd row, but the odd rows are 0. So D2 is 0. Now, if D2 is 0, that means, okay, now, what about D3? Yeah, D3 is going to go down 2 and go across 3. So 1, 2, 3. D3 is going to go from here to here. And that's also 0. So D2. You see, D2 is 0, so this picture is also E3. And then D3 goes here. So D3 is 0. Okay? And the reason now is that D3, it goes across 3. So it goes from an even column to an odd column. But all the odd columns are 0. So D3 is 0. Okay? So D2 is 0, D3 is 0. And D4, what's D4? Yeah, why is D4 0? Yeah, because it goes down 3. If it goes down 3, then it will be 0. It will go outside the first quadrant. And D5 will be 0. It goes down even more. So you see, actually, D2 is going to be, E2 will be equal to E3, equal to E4, and so on. And so it will be E infinity. So E2 equals E3 equals E4. Okay? So this is the picture of E infinity. Okay? And E infinity gives you the association. 1 is 0. Yeah. So that says D2 intersect H2 is ZU. Okay? It's a subgroup of D1 intersect H2, and the quotient here is 0. So this is also equal to D1 intersect H2. Okay? So D1 intersect H2 is a subgroup of D0 intersect H2, and the quotient is ZY. And so therefore, we have an exact sequence ZU. It's inside this. Okay, that's H2. And the quotient is this, ZY. So what's H2? If you have an exact sequence like this, it is the direct sum, because you have a free group here. Okay? So since ZY is free, it's a free abelian group of rank 1. H2 is ZU plus ZY. And then what's H3? Okay, H3 of S2, S1. Well, it's 0 because there is nothing in degree 3. And then in H4, you also have two non-zero terms. So it's going to be exactly the same as this argument. Okay, so what is H4 going to be? ZUY direct sum ZU square. Yeah, so in general, you see that in the odd degree, it will be 0. And then in the even degree, h of 2n S2, S1 will be Z U Y to the n minus 1 plus direct sum Z U n. Okay? And, pardon? Oh, sorry. Yeah, that's right. Un minus 1 y. Z U n minus 1 y. Okay? And so you can say that the equivariant cohomology of S2 is you have you start with 1, okay? So you have 1, and then ZU squared, ZU cubed, and okay, and then you have the ones with y, so you have ZY, Z UY, ZU squared y. Okay? Okay, now this first term, that's just the polynomial ring generated by U. Okay? And then the second term, everything has a y in it. So it's y times the polynomial ring. Okay, I'm going to write it this way, as the polynomial ring in U times y. And then we know that the degree of U is equal to the degree of y is equal to 2. Pardon? Oh, yeah, right. This is Z times 1. Yeah. Okay, good. Yeah, so this is the answer. Okay? That's the equivariant cohomology of the sphere under rotation. Now, when we calculated the cohomology of CP2, we actually got the ring structure, right? Because we know how the elements multiply. It's a polynomial ring in U, where U3 is set equal to 0. We have the ring structure. But here, we don't have the ring structure, okay? This is an isomorphism as abelian groups. So, you see, you can also write this as the polynomial ring generated by y over zu, okay? And then you set y squared equal to, the thing is, yeah, here's the problem. We don't know what y squared is, okay? I mean, y squared is equal to 0 in the cohomology of S2. But y squared may not be 0, you know, in the cohomology of the total space. So y squared is degree 2, so it has to be some linear combination of y and u. So, y squared is degree 4, so it has to be some linear combination of uy and u squared. Yeah, so there's some relation like that. If you know what the A and B are, then you know the ring structure, okay? Because then you know how to multiply y with itself. That's the only thing we don't know. I mean, y times u is going to be uy. It's there. So we don't know what yeah. Mm-hmm. Oh, yeah.
But you mean that the restructured in U is preserved?
Pardon?
How do you know that U, if you time U with another U, and U will vanish?
Well, u times u is u squared, right?
But how do you know that in this ring? I mean, it just that U squared is just a manual generation. Doesn't mean that.
Okay, it's because, the cohomology of the base injects into the cohomology of the total space. Yeah. So I need to prove that when there is a fixed point. And then we do have two fixed points. So, yeah. So there's a theorem. Theorem if G acts on M with at least one fixed point, then the cohomology of the base, which would be BG, injects into the equivariant cohomology of M. Okay, so yeah, so it shows that we need to prove a few general theorems about equivariant cohomology. Okay. Mm-hmm. And we need to develop some tools in order to figure out what the ring structure is. Okay. So let's look at some general theorems. About equivariant cohomology. Now, the first theorem is if you have a map of G spaces and it is G equivariant, then there's an induced map. Okay? So let NM be left G spaces if F from N to M is G equivariant, then there is an induced map Fg from the homotopy quotient of N to the homotopy quotient of M given by, okay, yeah, so you have EG cross N mapping to EG cross M, and then there's an obvious map, right, that takes EN to E F of N, and then you show that it's well defined when you go to the quotient. So, okay. So how do you show that it's well defined? Well, you pick another representative. Oh, that's right. Yeah. Okay. Now G always acts on EG on the right, right? And it acts on N on the left. Okay. So this is the same as this. Because they're equivalent. Therefore, the equivalence classes are the same. And then this one is going to go to E.g. F of G inverse N. Okay. But F is G equivariant, so that means that G comes out. And this is the same as this, right? Yeah, so this shows that it's well defined. So you have an induced map on the homotopy quotients that's well defined. And now, if you have a G space, you can map it to a point. Okay? And G acts on the point trivially. It takes a point to itself. So this map is equivariant. There's only one map like this. Everything goes to a point, and it's G equivariant. So there's an induced map on homotopy quotients. Okay. Now, what is the homotopy quotient of a point? Yeah. It's BG. You See, so the homotopy quotient of a point is EG cross a point, and then you divide by G. But EG cross a point is diffeomorphic, or sorry, not diffeomorphic, it's homeomorphic to EG. And so this is just EG over G, which is BG. Okay? So you have a map from MG to BG, and there is an induced map in cohomology. FG induces a homomorphism in cohomology going in the opposite direction. So it goes from H star of PG, H star of the homotopy quotient of a point to H star of MG. Okay? And this is the cohomology of BG. And this is the equivariant cohomology of M under G. Okay? Now, the homomorphism is a ring homomorphism. So you have a ring homomorphism from H star of BG into here. That means this is more than a ring, right? It means that you can use this as your scalars. You can multiply by these things. So they are your scalars. And so what does this, so this gives this ring another algebraic structure. What is it? Yeah, it's a ring, and it's also a module over this ring. Okay, so this makes the equivariant cohomology into an H star of BG module. Okay? And it's a ring, and it's also a module over H star of BG. So that's called an algebra. An algebra is a ring that's also a module over some other ring. So HG star of M is an H star of BG algebra. Okay. So equivariant cohomology has a very rich algebraic structure. It's a ring, but it's also a module over the equivariant cohomology of BG. And BG is the base of the universal bundle for the group G, and it's called the classifying space for G. So BG is the base of a universal bundle EG over BG for the group G, and is called the classifying space. we can say the, because it turns out that all the different BGs are homotopy equivalent. So there is really only one. Okay? And we already have some examples. So BS1 is S infinity. Okay? Sorry, no, CP infinity, yeah. BS1 is CP infinity, okay? Now, what other examples do we have? BZ, right? What's BZ? BZ is S1, okay? Because you have R over S1, which is the universal bundle for Z. Okay? And yeah, so you see that actually it's important to know what BG is for different groups. Okay? And then it's important to know how to calculate the cohomology of BG. Okay? So let me see. Yeah. So there are some general theorems, and yeah. So let's try to say work out B of O K. Okay. B of O K, the orthogonal group. Mm-hmm. This will give us quite a few more examples. Sorry, I should do this. B of OK. So we're going to generalize B of S1. Okay? S1 is SO2. Mm-hmm. Mm-hmm. And SO2 has the same universal, the same total space for the universal bundle as O2. And we know that it's S infinity. Yeah, so we have to generalize S infinity. Now S infinity, well, came from Sn. So the generalization of Sn is Stiefel varieties. Okay? So now Stiefel varieties, VKN, it's the set of all orthonormal K-frames in Rn. Okay? Okay, now what's a K-frame? A K-frame, it's just K-linearly independent vectors. A set of K-linearly, an order set of K-linearly independent vectors. Okay? So now, so a K-frame will span a K-dimensional plane. So a K-frame spans a K-plane. And what's the set of all K-planes in Rn? That's the Grassmannian, yeah. So, there exists a map from VKN to GKN whose by just sending that K plane to the plane, it spans, right? And so the fiber would be all the different bases, orthonormal bases of a K plane. Whose fibers is all the orthonormal bases of a K plane. Okay? And all the different bases can be obtained from each other, right, by an orthogonal matrix, a K by K orthogonal matrix. And so i.e. the fiber is going to be OK. Okay? Yeah. So this will be a fiber bundle with fiber OK. And so it generalizes, okay, yeah. It generalizes. You see, if K is 1, then what is V1n? What's V1n? That's like orthonormal, one frame. That means a unit vector. So this is unit vectors in Rn. So this will be Sn minus 1. Yeah. Okay. Yeah, it doesn't quite generalize BS1 because there we are using complex projective spaces, and here G1n is real projective space. Because it's all the line through the origin in Rn, so that's Rp n minus 1. Okay. Okay, and then, so then obviously we're going to take the union over all n, and that will give us the infinite Stiefel variety, and then our hope is that it will be weakly contractible, so we have to compute its homotopy groups, show that it's all 0, and then it will give us the universal bundle, right? So I'm going to stop here now, okay? Yeah, and you can read about this in the book. And, okay. So problem set 2 is due in 2 weeks, and it's many computations using the spectral sequence. So I want you to get some practice calculating using the spectral sequence. And, if you have problem set 1, you can hand it in now, okay? Yeah. I think I probably assigned too many problems, so if you didn't do them all, it's okay. Yeah. Yeah, good. Thank you. Okay, thank you. Thanks. Thank you. Okay. Yeah, any more? Thanks. Okay. All right. Yeah. Okay, so I'll see you on Friday at 12:20.